Okay, we're going to start chapter 3 on probability. We're going to break this up into the 3 sections. This first section is covering an introduction to probability and just getting used to the terminology that we're going to use as we go along. So we'll start off with what we mean by probability. And probability is always going to be a number, either a fraction, a decimal, or a percentage between or including 0 and 1. So that's inclusive. And it is going to give the likelihood or chance an event will occur. If the probability is 0, then there is no chance that it'll occur. So if it's 0, no chance, and a probability of 1, find someplace to put that. Probability of 1 means it will occur with no chance that it won't. So it will occur for sure. We want to define experiment for our purposes, and then we're going to define it specifically for statistics. An experiment is any activity or process of observation that leads to a single outcome that cannot be predicted with certainty. So we're expanding what we mean by experiment from sort of the clinical or the lab setting in sciences to be any activity or process that we don't know how it's going to end up. In statistics, we're going to define it even more narrowly, and we're going to say an experiment often is taking a sample from a population. We do not know what sample we're going to get when we go through the process of surveying or experimenting to get a sample from a population. So that falls under that definition of experiment. So examples would be if we survey graduates for the number of job interviews they've had. Okay, we don't know what responses we're going to get from that survey. We don't know what members we are going to get from the population to be in the sample. It's not certain. All right, other things, obtaining blood types from a group of individuals, measuring the length of bridges in Oregon, asking a sample of students if they have had a flu shot. These are all experiments because we don't have certainty about what the result is going to be when we do those. Okay, so we're going to just kind of run through some more definitions. We're using a really simple example, probably the classic, most simple probability example, and that is taking the experiment of rolling a fair six-sided die. So we want to look at events that can occur in rolling that six-sided die. Okay, first thing we want to look at is sample space. A sample space of an experiment is the set of all possible outcomes. So for rolling a die, we'll say S, the sample space is the set, and we'll use these braces to indicate that set. We can get 1, 2, 3, 4, 5, 6. Okay. All right, that is the sample space. It includes all the possible outcomes. Now, the other thing I want to go back to experiment and just highlight one of the aspects of that definition is that an experiment can only result in one outcome. So when we roll a fair die, we're only going to get one of the outcomes listed here. It's only going to equal one number. All right, next thing we want to do is calculate probability. So if we want to calculate the probability of an event occurring when all the outcomes in the sample space are equally likely. So that is like rolling a fair die. It's equally likely that we're going to get any one of those values when we roll a die. So to come up with a probability, we count the number of outcomes in a particular event, and then we divide the total, we divide that by the total number of outcomes in the sample space. So if we want to look at that kind of formulaically, if we have an event that we're calling A, to get the probability of A, which is what this stands for, the probability of A, we just take the number of outcomes in that event and we put that over the total number of outcomes in the sample space. So we could kind of add that in S. Oops. Okay. All right, so let's find the probability of our sample space, S. Well, there are 6 outcomes in the sample space, and we put that over the total number of outcomes in the sample space, and we get 6, and we get 1. Okay, so we can write that as 1. We can write that as 100%. There's a 100% chance that we're going to get one of the outcomes in the sample space if we roll that die. Okay, and that's always going to be the case. If we take the probability of the sample space, we're going to get a 1. Okay, now this isn't in this question, but what if we want to find out what's the probability that we roll a 10? Okay, well, there are 0 10s in the sample space over the 6 possible outcomes, so that's 0, or 0% chance that we're going to roll a 10 when we roll a die. Okay, let's look at number 2. Event A is the event that the outcome when we roll the die is an even number. First thing we want to do is define the event, list out the outcomes that satisfy. That's 2, 4, and 6. All right, so that lists out the event. And then we want the probability of that event. So there are 3 outcomes in event A over the total of 6. You get 3 over 6, so we write it as 1/2, or I won't do this every time, but we can write that as 0.5 or 50%. All right, next one, event B, the outcome is less than 5. First, listing out the outcomes that are in that event. We get 1, 2, 3, and 4. 5 is not included. We only want values that are less than 5. Okay, finding the probability of that event B. All right, we just take that 4 over 6 and reduce that. We get 2/3. Okay, or we can write it in decimal form. All right, it would be 0.33. We would round that to say 2 decimal places, and we get 30.33. Okay, let's look at one more event, and then we'll define some other things. The event C, the outcome is 4, so we get a single outcome in that event. And taking the probability of that event, you get 1 over 6, okay, for that probability. Sorry about that. Let's define complement of an event. Complement of an event A is all the outcomes that are not in A, and we denote that with A prime. So if we remember, A is all even numbers, so A prime, the complement is the odd numbers, 1, 3, and 5. And the probability of A prime is 3 over 6, or 1/2. All right, let's look at C prime. So the complement of C. C is just the outcome of 4, so C prime is 1, 2, 3, 5, 6. And that probability is 5 outcomes over the 6 total. Okay, let's look at another kind of event, AND event. This is where we take 2 events, A and B, and we combine them with and that is going to include all the outcomes that are in both A and B. So we can think of the AND event to be the overlap between the 2 events. So if we remember, A is 2, 4, 6, B is 1, 2, 3, 4. So for this event, A and B, we are looking for the outcomes that are in both. So 2 shows up in both and 4 shows up in both. So this AND event is just the 2 outcomes, 2 and 4. And the probability of A and B is those 2 outcomes over the total, 2, 6, which we can reduce to 1/3. Let's try this next one. A prime and C. Okay, remind ourselves, A prime is 1, 3, 5. C is 4. So if we want this outcome, or this event, A prime and C, we look and see there are no shared outcomes. So we've got braces with nothing in them, or we can write the empty set symbol, or say it's empty set. And if we look for the probability of that combined event, that is 0. There's no way that we can get A prime and C both occurring at the same time. Let's get back. Now let's look at this event, the OR event. It takes 2 events, A and B, and it combines them and includes the outcomes if they are in A or in B or in both A and B. So it's more inclusive than the AND event. So if we look at A or B, all right, remember A is even numbers, B is less than 5, so the outcomes are going to be 1, 2, 3, 4. Okay, that gets everything in B, and it gets 2 and 4 from A, and we want one more outcome, and that is 6. And so then our probability of A or B is 5 outcomes over 6. 0.5. Okay, all right, let's look at the next one. We have the OR event C or B prime. Reminder that for C, we've got 4 is in the sample space, and B prime, complement of B, that will be 5 and 6. All right, so if we want to find this event, A or, oops, not A, C or B prime. All right, we're going to include all of the values in C and B prime. So that's 4, 5, and 6. So even though they don't share any events, because we have that OR event, which is very inclusive, we include all of them. So now let's find the probability of C or B prime. There are 3 outcomes out of the 6, so we get probability of 1/2. All right, okay, now let's look at conditional probability. Conditional probability assumes that one event has already occurred, and the notation here, probability of A, that vertical line, we want to read that as given. So whatever is given, we're assuming that it's already occurred. So the probability of A given B assumes that B has occurred, and we're looking for the probability of A. And the effect that that has on calculating the probability is that we change the denominator. So we have been putting the number of outcomes in the sample space in the denominator. Well, we now are assuming that something's already occurred, that given event. So the denominator now becomes the number of outcomes in the given event. So in this case, it's 4. Now we're assuming that has occurred. So the numerator is going to be the number of outcomes that are in A and B. So only outcomes that are shared, that are in the AND event, can now occur from A. So we'll put in, for the numerator, number of outcomes in the AND event A and B. All right, we determined that was 2, so we get 2 over 4, or a probability of 1/2. Okay, let's look at the probability of B given A. We have the same events, but it's not going to be the same because we're assuming that A has occurred now. So the denominator becomes the number of outcomes in A, which is 3, and the numerator is still the number of outcomes that are shared between A and B. All right, so we get 2 over 3, or 2/3 for that probability. Let's look at a couple more. So we got the probability of B given C. So we're assuming that C has occurred, and if we remember what that event C is, it is that one outcome of 4. So the denominator is just 1. It gets shrunk down to 1 outcome. B is 1, 2, 3, 4. So if we look at the AND event between those, right, it's just the 4. So we get 1 over 1. So probability of B given C is 100%. So if C has occurred, then B will occur with 100% probability. All right, let's go the other way. A probability of C given B. So 4 outcomes in B, so that becomes the denominator. That given event always gives us the denominator, and then the shared number of outcomes is 1. So we get 1/4, or if we want to put that in decimal form, 0.25. All right, so far we've been looking at these examples where we have an experiment that has outcomes with equally likely probability. So we're going to look now where we are given probabilities of events occurring to kind of figure out how to find these conditional probabilities. So one little change here, this should say the probability of A and B over probability of B. That's left over from a previous textbook. Okay, so if we have 2 events, A and B, we're assuming the probability of B is greater than 0, then we're going to define the conditional probability of A given B by not taking number of outcomes in the numerator and denominator, but we're looking at the probabilities of the events occurring. Okay, so same as we were looking at before, by dividing by the probability of the given event, we're shrinking down the sample space to reflect that that event has already occurred. So let's look at probability of A given B for this example. Okay, so we know we're going to need a numerator and denominator. The denominator comes from that given event. In this case, that probability is 0.77. The denominator, or the numerator, is the probability of the AND event. That's given to us as 0.32. So we plug that in our calculators, we're going to get 0.4155, and it keeps there keeps being values there. If we round that to 2 decimal places, we get 0.42. Let's look at another example. This is based off this online class. 55% of the students are nursing majors, 50% are sophomores, and 25% are nursing majors and sophomores. We want to find some probabilities that a randomly selected student is a nursing major if he or she is a sophomore. So we have a little bit different wording here. We want to recognize that what we have is a conditional probability. So we're assuming that the student is a sophomore. So the sophomore is the given event here. So we're looking for the probability that the student is a nursing major, given that we know that they're a sophomore. So the sophomore probability is what goes in the denominator. 50% are sophomores, so the probability that we select as sophomore is 50%. And the probability that we get a nursing major and a sophomore is that 25%. So we get probability of 1/2. We get probability of 1/2. Okay, let's look at this next one. A randomly selected student from all nursing majors is a sophomore. So this time, the nursing major is what is given. We want the probability of selecting a sophomore given we know that the student is a nursing major. So the probability of being a nursing major goes in the denominator, and we get the same numerator. It's the probability sophomore and nursing major. This gives us probability of repeating 0.45, so that's going around to 0.45 if we go to 2 decimal places. The last thing that I want to go over in this section 3.1 is not actually in this section in the textbook, and we're not going to officially cover it, but Venn diagrams can be helpful in understanding some concepts. So I'm going to cover it, and I will use it in the next 2 sections, and it will be available for you to use as you work through exercises in this chapter. But again, we're not going to be officially you're not going to be officially held responsible for it. Okay, so a Venn diagram is just a way that we can have a visual, a picture of a sample space and events and the relationship of those events. So the box, the rectangle, represents the sample space. So we could even label all these rectangles with there's the whole sample space of whatever the experiment is that we're doing. And then we can represent events with circles that then we label. Okay, next thing we want to think about is, well, if the circles represent the events, how do we represent the events that are we get by combining these 2 other events? So the event A and B. So remember, that's the event that we get if we look at the overlap of the 2 events. So if we look at the overlap, it's only going to be this piece where there's overlap in circles. Okay, so that red shaded spot right there represents that event A and B. All right, and if we look at OR, so remembering OR is more inclusive. It only has to be in one of those events to be included. So it's going to include all of A and all of B. So we shade, fill in all of that. Okay. All right, now let's look at A prime. So that's the complement of A. So that's going to be everything except for that circle that represents A. So it includes all of B except for the overlap piece, and then it includes the whole rest of the rectangle that are not in either of those events. Okay, now let's look at these conditional events. So A given B. All right, so if you remember, what we said was if we have a conditional event, we are assuming that one of the events has occurred and that becomes the new sample space. So we actually have to pull that given event B out of the sample space, and that becomes its own stand-alone sample space. But it brings along with it this little slice, right, which is the A and B. All right, so that little piece is A and B. Okay, and that's also what represents the probability of A given B, is that little slice. Okay. This next one is probability of B given A. So really similar. A is given, so that becomes the new sample space. Also brings with it this little slice that represents A and B. So that conditional probability then is going to be that little slice. Okay, in the sections to come, I will a couple of times refer to Venn diagrams, and we'll use those pictures to kind of help us move forward.